Good evening, sir.
Good evening, ma'am.
Sir, you can start, sir.
Enable me, ma'am. Ma'am. Hello, ma'am.
Good evening, sir.
Yeah,
Yes, sir.
enable the sharing, ma'am.
Sir?
Screen sharing, enable, make me the host, ma'am.
Yes, sir. This is.
Good evening, sir.
Yeah, good evening. Good evening.
Sir, you can continue, sir.
Yes, ma'am. Good evening, all of you. Ritika is there. And Lakshmi is there. Ritika?
Yes.
Yeah,
Sir.
very nice. Yeah. What, Ajay?
Sir, your voice is very low, sir.
I didn't talk anything. Now you can hear me. Now is it audible?
Sir, yes, sir.
Yeah. All right, we'll continue with what we were doing yesterday. All right, few more questions based on Cole-Rush's law, and the next part of the topic we will do it. And I have to solve a few more questions on these topics. That is later part. Once we complete the theory part of it, we will concentrate on few more questions or repeatedly asked questions or type of question we will learn. That is later part. Cole-Rush's law. Limiting molar conductivity for some ions is given below in Siemens centimeter square per mole. Sodium ion 50.1, chloride ion 76.3, hydrogen ion 349.6, acetate ion 40.9, calcium ion 119.0. What will be the limiting molar conductivity of calcium chloride? Sodium acetate, this is capital H, and NaCl. They're asking three questions are there. They're asking molar limiting conductance of calcium chloride, sodium acetate, and NaCl. Now, molar limiting conductance of calcium chloride will be equal to?
Sir, it'll be the limit. So it'll be the molar conductivity of calcium plus 2 into the conductivity of chlorine.
Correct. So it'll be what? Calcium is what they've given. 119.
Sir, 119, sir.
Plus chlorine
so
is what?
2 into 76.3.
That will be equal to around 271.6 Siemens centimeter square per mole. Likewise, what will be the molar conductance of acetic acid? Sodium acetate, sorry. Sodium acid, very simple question it is. Molar conductance of acetate ion. Acetate ion plus what? Molar conductivity of sodium ion. Acetate ion is 40.9 and chloride ion is 76.3. It will be equal to around 91 point something Siemens centimeter square per mole. And similarly for NaCl, it is very simple. NaCl is conductance of Na plus ion plus Cl minus ion conductance. All is limiting molar conductivity, lambda naught. Sodium ion, they've given us 50.1 and chloride ion is 76.3. So that will be equal to 126.4. So the answer for this question is option C. Option C. Getting it? Are you with me?
Yes, sir.
Yeah. Let's see how do we work this problem. Now, equivalent conductance of NaCl, HCl, and sodium ethanoate. Not ethanoate, what's this called as? What is this? Yeah, ethanoate, it's an ester. Sodium ethanoate, not ethanoate, man. What is this? C2H5 Acetate is CH3COO minus. Acetate
The
is CH3.
propanoate.
Propanoate, sodium propanoate, 3 carbon atom, no sodium propanoate. Good. At infinite dilution are 126.4, 426.16, and 91 per ohm per centimeter square, respectively. The equivalent conductance of propanoic acid is propanoic acid. How do you work? Lambda infinity of NaCl is equal to lambda Na plus lambda Cl minus. We'll mark this as equation number 1. Now, again, conductance of HCl at infinite dilution is given as lambda H plus of lambda Cl minus lambda. This will mark it as equation number 2. The third one, lambda infinity of sodium propanoate, C2H5CONA. That will be equal to lambda Na plus lambda propanoate ion, C2H5CO minus ion. This is equation 3. Now, what's that we need? From these 3 equations, we need to get the conductance of water, C2H5 of propanoic acid. We have from these 3 data, we need this. So how do we get this? How do we get this? In order to get this, what we're supposed to do is equation 2 and 3, we need to add and subtract equation 1. And then subtract equation 1. When I add 2 equations, 2 and 3, what happens, you see? So 2 and 3, when we add, what you will get? You get lambda HCl plus lambda C2H5COONA plus, not plus, minus the first equation, lambda NaCl. So what happens? See, this is a minus sign. Here, this Cl and this Cl will get cancelled. This Na and this Na also gets cancelled. What else you have? You have C2H5COO and you have H. So that's nothing but propanoic acid. So in order to get the molar conductance of propanoic acid, C2H5COOH, you have to add the HCl and the sodium propanoate and subtract the NaCl. So what's the conductance of HCl? They've given 91 plus, what is the conductance of, this is for HCl. What's the sodium, this is the conductance of, sodium propanoate. HCl is, what happened? Can you see the screen? Students, can you see the screen?
Yes, sir.
Yes, sir.
Hey, okay, on it. I am not able to. Okay. Now, this is 91 is for sodium propanoate. For HCl is 426.
So
426.16 plus 91 minus of 126.45. On simplifying this, the answer will get us 390.71 per ohm centimeter square. Therefore, the answer for this question will be option B.
So B, sir.
Option B. Anyways, now Cole-Rush's law problems, did you understand? These kind of problems they can ask you. Okay, we'll work few more problems based on Cole-Rush's law, all that after the end of the chapter. Different types of questions we will solve from different material. Now, so far, I hope that you followed. Yes?
Yes, sir.
Yeah. Now we will learn the electrochemical cell, the cell representation, salt bridge, all that. What all is there, we'll see. Presentation of a cell. All right. So, now what is an electrochemical cell? This electrochemical cell is also called as galvanic cell. It's also called as voltaic cell. Galvano is the person who invented this. Therefore, it is named on him, galvanic cell. Since we can measure voltage, we call it as voltaic cell. Now, electrochemical cell or galvanic cell is a device in which a spontaneous redox reaction is used to convert chemical energy into electrical energy. A cell which converts chemical energy into electrical energy will be called as an electrochemical cell. Now, for examples for electrochemical cell, we can mention one of the examples is Daniell cell. Not only Daniell cell, we can talk about dry cell. The battery is what we use for the watches or other materials at home, wall clocks. all that. Those are made up of dry cells. So dry cell, Daniel cell is an example for electrochemical cell. What's an electrochemical cell? Electrochemical cell or a galvanic cell is a device in which spontaneous redox reaction takes place to convert chemical energy into electrical energy. Now, characteristics of an electrochemical cells. Following are the important characteristics of electrochemical cell. What is that characteristic? We will learn the characteristic a little later. We will try to understand the construction of electrochemical cell, construction and working of an electrochemical cell. Now, this electrochemical, firstly, in order to understand an electrochemical cell, we need to understand a term called as electrode. Now, what is an electrode? A metal dipped in its own ions is called as an electrode. What is an electrode? A metal dipped in its own ions is called an electrode. What do you mean by that? Now, for an example, I have a beaker. In this beaker, I have zinc ions. If a zinc rod is dipped here, then this will be called as zinc electrode. Now, if we take ions, Au3+, auric ions, gold ions, and gold metal is dipped here, this will be called as gold electrode. Likewise, if we have a copper ions, and if copper rod is dipped, this will be called as copper electrode. If we have silver ions here, and if silver rod is dipped, it is called as silver electrode. So what is the definition of an electrode? Metal dipped in its own ions is called as an electrode. What is the definition for an electrode? Metal dipped in its own ions is called as an electrode. Now, the next definition, what you have to understand, is called as electrode potential. This electrode potential is represented by a letter E. What is this electrode potential? Now, if you take any of the electrodes, what we have spoken here, this metal and the ions will be in equilibrium. That means copper will be in equilibrium with copper 2+ ions. Copper 2+ ions. That means there is a contact, there's an interface. Interface means junction, at which the metal is in contact with its own ions. At this junction, there will be a potential developed. That potential is called as electrode potential. What is this potential? Electrode potential. Potential developed when the metal is in contact with metal ions at equilibrium. Is called as an electrode potential. What is electrode potential? They can ask you for 2 marks. What is electrode potential? So electrode potential is defined as a potential developed when the metal is in contact with its metal ions at equilibrium. See here, metal is in contact with its metal ion. At what point? Equilibrium. That time a potential will be developed here between the metal and the metal interface with the metal ions. That is called as what? Electrode potential. This electrode potential is represented as E. Now we have one more called as standard electrode potential. Now what is the standard electrode potential? The standard electrode potential is represented as what? E0. So it's the same definition. Potential developed when the metal is in contact with its own ions at equilibrium and at what temperature? 25 degrees Celsius, and the concentration of the electrolyte to be what? 1 molar. If the concentration of the ion is 1 molar and the temperature is what? 25 degrees Celsius, that time whatever the potential we measure is called as what? Standard electrode potential. Did you understand what it is?
Yes, sir.
Yeah. Now, 3 definitions we learned. One is electrode potential. We learned the other one as what's an electrode first. The second one is electrode potential. The third one is standard electrode potential. Now, standard electrode potential is defined as the potential developed when the metal is in contact with its own ions at equilibrium and at 25 degrees Celsius and 1 atmospheric pressure. That's called a standard electrode potential. No problem with this? Students, everybody followed?
Yes, sir.
Others?
Yes, sir.
Yeah, please tell me. All right. So now we have to learn the characteristics of the electrochemical cell. We will learn the characteristics of the electrochemical cell in few minutes now. In order to understand an electrochemical cell, you should know what is an electrode. That is why I defined what is an electrode. And also we defined what is an electrode, potential, all that we learned. Standard electrode potential, all that we learned. Now we will try to understand the characteristics of an electrochemical cell. Now, in order to understand the characteristics of an electrochemical cell, we will learn the construction and the working of Daniell cell itself directly. So they'll ask you, explain the construction and working of Daniell cell. Daniell cell is an example for an electrochemical cell, Daniell cell. Now, in order to construct a Daniell cell, we require two electrodes. One will be a zinc electrode, the other one will be copper electrode. So in order to construct Daniell cell, how many electrodes are required? Two electrodes. One will be the zinc electrode, the other one will be copper electrode.
So,
see, zinc electrode is placed on the left-hand side. Zinc electrode is placed on the left-hand side. What do you mean by zinc electrode? Zinc rod in contact with what ions? Zinc ions. Now, when I say zinc ions, it can be of zinc sulfate. Zinc ions will not exist individually. It has to exist as a compound, zinc sulfate. Now, the other electrode is the copper electrode. Now, when we say copper electrode, copper ions we can get it from copper sulfate. Copper ions in contact with what rod? Copper rod. So this will be called as copper electrode. These two electrodes are connected externally by means of an insulated copper wire. These are connected externally by means of an insulated copper wire through voltmeter. Voltmeter or voltammeter is an instrument used to measure the voltage. So what did I tell? Zinc electrode and copper electrode is connected externally by means of an insulated copper wire through voltmeter. Insulated copper wire, you know, for mobile charging also you have a charger wherein the wire is insulated, all right, plastic, otherwise it's difficult to use. So insulated copper wire through voltmeter. And these two electrodes are connected internally by means of a salt bridge. This is a salt bridge, a bent tube containing certain components. We will learn about it. All that, what is salt bridge itself in detail, we will have to learn. So this is the representation of a Daniell cell. What is the construction of Daniell cell? In 2 or 3 points, if I have to tell, what is that? The first point, zinc electrode and copper electrode are connected externally by means of an insulated copper wire through voltmeter. Second point, they are both connected internally by means of what? A salt bridge. Did you understand this?
yes.
Yes, sir.
Yes. Now, zinc electrode is a positive electrode. Zinc electrode is a anode. Zinc electrode is what? Anode. Copper electrode is cathode. Copper electrode is cathode. Now, firstly, in the electrochemical cell, you should remember whatever is represented on the left-hand side is anode. Whatever electrode is represented on the left-hand side is what? Anode. Anode is what electrode? Anode is what electrode? A positive electrode. Anode is what electrode? Positive electrode. But we are represented by what sign? Negative sign. Cathode is a negative electrode represented by what sign? Positive sign. All right. So the electrode which is placed on the left side will be always anode. At anode, always what takes place? At anode, always oxidation will take place. And at cathode, always the reduction will take place. So whatever electrode which is placed on the right-hand side, it will be cathode. Cathode means reduction. Anode means oxidation. And red cat, we started electrochemistry chapter like this. So this is the construction of what? Daniell cell. So what is the construction? How do you construct a Daniell cell? Daniell cell is constructed by using zinc electrode and copper electrode. The zinc and copper electrode are connected externally by means of an insulated copper wire through voltmeter. They are connected internally by means of a salt bridge. Anode A zinc electrode is considered to be anode, and copper electrode is cathode. Anode is a positive electrode, but it's represented by minus sign. Cathode is a negative electrode, but represented by positive sign. Now, what happens at anode? What should take place? At anode, oxidation should take place. What is oxidation? What is oxidation?
Sir, removal of ions, sir.
Loss of electrons, not ions. Loss of electrons is called as oxidation. Now, zinc electrode we have. The zinc electrode will lose electrons, 2 electrons to form the zinc 2 plus ions. That means the metal zinc here will dissolve here. Metal zinc, this metal zinc rod will dissolve here to form the zinc ions, 2 plus ions. These electrodes which are given by anode, since electrons are lost, we represent negative sign for anode. These electrons move towards cathode using the external wire. These electrons, which is donated by zinc, move towards what? Cathode using what? The external wire. At cathode, what takes place? At cathode, reduction. What do you mean by reduction? Reduction is nothing but gain of electrons. Now, reduction at cathode, what you have? CO2 plus ions you have here. CO2 plus ions. These 2 plus ions will accept the electron given by zinc. These electrons are given by zinc, accept this electron, and it will get reduced to copper. That means here metal will anode, there will be dissolution of metal. So when you add these two equations, what we get Zn plus CO2 plus, giving you Zn2 plus C. So this is the reaction because these two electrons will get cancelled here. So therefore, this is the overall reaction. This is the overall reaction. Did you understand the overall reaction? Did you understand the overall reaction?
Yes, sir.
Yes, sir.
Yeah. Now you have to understand certain things here. When I say we have to understand certain things here, now cell representation. How do you represent a cell? Now, before we understand how we represent a cell, we will learn what is a salt bridge. Salt bridge. Now, the salt bridge is a bent glass tube. The salt bridge is a bent glass tube. In this bent glass tube, we will have saturated solution of ammonium chloride, or we will have potassium nitrate. Potassium nitrate. Only these three things can be used in order to prepare a salt bridge. What is the salt bridge I told you? It is a bent glass tube which contains saturated solution of KCl, ammonium chloride, potassium nitrate in a jelly called as agar-agar jelly. In agar-agar jelly. So to hold these ions, we need to have a gel type material. That is a natural material available, so that's called as agar-agar jelly. Now, this salt bridge, what we're talking about, what's the importance of salt bridge? All that we will learn. Now, salt bridge is made of, assume that KCl. Now, when I say KCl, potassium is positive charge and chlorine is negative charge. So chlorine will go to anode and potassium will move towards cathode. Now, the ionic mobility, why are we not using HCl? Why are we using only KCl, KNO3 or ammonium nitrate, ammonium chloride? Why not anything else? See, hydrogen ion movement is very fast compared to chloride ion. So since hydrogen ion movement is more, if I use HCl, H plus will move towards cathode more easily compared to Cl minus. That means at cathode, more H plus ions will be there. At anode, less chloride ion will be there. There will be charge difference there. So assume at 100 H plus ions move here and 10 Cl minus ions move towards anode. So what happens? More positive ions will be here at cathode. Therefore, what happened? There is a fluctuation in what? The voltage. That is why we cannot use HCl. Now, the speed at which potassium moves, the same speed chloride also moves. So if 10 chloride ion moves towards anode, 10 potassium ion move towards cathode. Therefore, there is a charge neutralized. That is why we are using what? KCl or what? We are using what? Was it ammonium chloride or potassium nitrate? No other things can be used in what? Salt bridge. Did you follow the importance of salt bridge?
Yes, sir.
Yes, sir.
Yes. Now, cell representation. How do you represent a cell? Always remember cell representation. It is represented, anode is represented on the left side. Anode is represented on the left side, and cathode is represented on the right side. And these anode and cathode is separated by a salt bridge. Anode and cathode is separated by what? A salt bridge. So how do we represent? The electrochemical cell? Anode on the left side and cathode on the right side. Both separated by a salt bridge. So salt bridge is represented by two parallel lines. Now in this case, at anode, what is happening in Daniel cell? Zinc is undergoing oxidation from Zn0 here charged to Zn2 plus. Zn2 plus. Zinc 0 to Zn2 plus. This is the interface between the metal and the ions. Copper is undergoing what? Reduction. Cu2 plus to Cu. These two are separated by what? A salt bridge. This is the cell representation. You can represent the concentration here also for zinc ions and copper ions. Did you understand the construction and working of the electrochemical cell, Daniel cell? I told you how to construct a reactions. See, each electrode is called as a half cell. Each electrode is called as a half cell. The zinc electrode is called as a half cell. Copper. Two half cells, when they combine, we get a one complete cell. And that's called as an electrochemical cell. So electrochemical cell is a cell which converts chemical energy into electrical energy. So many things we learned today. What happens at anode, what happens at cathode, the cell reactions, overall reaction, cell representation, the construction and working. Did you follow this?
Yes, sir.
Yes, sir.
Now see, the electrochemical cell consists of two vessels, two electrodes, two electrolytic solution, and a salt bridge. Two electrodes taken are made of different materials and usually set up in two separate vessels. All this is in detail. I explained it to you in the simple way. The electrolytes are taken in two different vessels called as half cells. Two vessels are connected by a salt bridge, porous spot. The electrode on which oxidation takes place is called as anode, represented by a negative sign because electrons are lost. Now, I forgot to tell you a point here. Now, the electrons move from anode to cathode. This movement of electron, loss of electron from anode and gain of electron from cathode appears as the current. So current flows from cathode to anode. You should remember, current flows from cathode to anode. So loss of electron is, or gain of electron is change in chemical energy. That change in chemical energy appears as electrical energy, or appears as what? Current. So current flows from cathode to anode. You should remember. I was not able to write it there properly. So in electrochemical cells, ions are discharged only at cathode. In electrolytic cell, in electrochemical cell, from outside the electrolytes, electron flow from anode to cathode, and current flows from cathode to anode. Just now I told you. That. All right. Next one is, for an electrochemical cell, E cell is positive. Electrode potential is positive. Free energy is negative. Delta G stands for free energy. This E cell is otherwise called as EMF of this cell. In electrochemical cell, the reaction is exothermic. In electrochemical cell, reaction is exothermic. And what is the type of reaction taking place in the electrochemical cell? What's the type of reaction taking place in the electrochemical cell? Redox reaction. So at anode, oxidation and cathode reduction. Both oxidation and reduction takes place simultaneously. Therefore, it's called as what reaction? Redox reaction. Followed?
Yes, sir.
Yes, sir.
Now you can see here the same thing what we learned. Salt bridge is a U-shaped glass tube filled with jelly-like substance, agar-agar, plant jelly, mixed with an electrolyte, potassium chloride, potassium nitrate, ammonium nitrate. Ammonium chloride also can be used. The electrolytes of two half shells should be inert and should not react chemically with each other. Electrolytes of two half cells should be inert. That means zinc sulfate and copper sulfate should not react. The cation as well as anion of the electrolyte should have same ionic mobility. I told you these all have what? Same ionic mobility. All right. That is why we are using only these three. K plus will move at same speed as Cl minus, and K plus will move at same speed as NO3 minus. Ammonium ion will move same speed as nitrate ion. Therefore, we are using the salt, using the salt bridge. It connects us. See, importance of salt bridge, important functions of salt bridge. Important. This question is important. What are the functions of salt? It connects the solutions of two half cells and completes the circuit. It connects the solutions of two half cells. See here, this is a salt bridge. This connects the solutions of two half cells and completes the circuit. First point. It prevents interference or diffusion of solution from one half cell to the other. The salt bridge prevents the diffusion of one electrolyte. This electrolyte and this electrolyte, they will not undergo diffusion. So that is prevented by the salt bridge. The third point is, right? The third point is, it keeps the solution of two half cells electrically neutral. I told you K plus will move towards cathode and Cl minus will move towards anode. Number of K plus and number of Cl minus moving towards the respective electrode is same. Therefore, it maintains electron neutrality. So that's what it means. It keeps the solutions of two half cells electrically neutral. Then it prevents liquid-liquid junction potential. What do you mean by this liquid-liquid junction potential? That is the potential difference which arises between two solutions when they contact with each other. So they prevent a liquid-liquid junction potential. And mention only this, it prevents liquid-liquid junction potential. Functions of salt bridge is important. It connects the two half solutions of two half cells and completes the cell circuit. It prevents transference or diffusion of solution from one half cell to the other. It keeps the solution of two half cells electrically neutral. It prevents liquid junction potential. That is the potential difference which arises between two solutions when they are in contact. Representation of an electrochemical cell, I clearly told you. Anode, oxidation, and represented by negative sign, and cathode is it undergoes reduction and represented by positive sign, and salt bridge. Not bridge, internally connected, but bridge. All right. Do you have any clarification with this? I'll have to work out some problems, all that little later based on these concepts. Tell me if you have any clarifications.
No doubt.
No doubt. All clear. Good. Now, others, are you there?
Yes, sir.
Oh, following.
Yes, sir.
Now, coming to the reversible and irreversible cell. A cell is said to be reversible if the following two conditions are fulfilled. A chemical reaction of a cell stops when exactly equal external EMF is applied. When exactly external EMF is applied. The chemical reaction of cell is reversed and current flows in the opposite direction when external EMF is slightly higher than that of the cell. Any other cell which does not obey the above two conditions is termed as irreversible cell. Daniel's cell is reversible, but this cell, zinc sulfuric acid Ag cell, is irreversible. Now, we'll try to understand this. A cell is said to be reversible if the following two conditions are fulfilled. What is that? A chemical reaction of the cell stops when an exactly equal external EMF is applied. Now, in case of Daniel's cell, now oxidation takes place at zinc and reduction takes place at cathode. This copper, current flows from cathode to anode, all that we were talking about. At standard condition, the potential developed is 1.1 volt. How much is the potential? 1 mark question for 12th standard. What is the potential developed in Daniel's cell? Or what's the EMF produced in the Daniel's cell? It is 1.1 volt. We will work out this problem later. Now, what happens? See, the potential developed is 1.1 volt. Now, if an external potential is applied, 1.1 volt in the opposite direction, if the external potential is applied in the opposite direction, 1.1 volt, so what happens? The cell reaction will stop. So those kind of reactions are called as reversible reaction. If you apply little greater than the potential observed, If you observe, if the potential is applied, external potential is applied greater than the potential produced by the cell, then the cell reaction is different. That means instead of current moving from cathode to anode, the current starts flowing from anode to cathode. These two conditions are called as required for the cell to be reversible. See, the external reaction of the cell stops when exactly equal external EMF is applied. The chemical reaction of the cell is reversed and current flows in the opposite direction when the EMF is slightly higher than that of a cell. Any other cell which does not obey these two conditions are termed as irreversible cell. Daniel cell is an example for reversible cell, and zinc silver cell is this electrolyte here is sulfuric acid. Zinc is an electrode, silver is an electrode. So sulfuric acid is an electrolyte. This is an example for an irreversible cell in cell. Types of electrochemical cell. Two main types of electrochemical cells have been reported. These are chemical cells. The cell in which electrical energy is produced from the energy change accompanying a chemical reaction or a physical process is known as a chemical cell. Chemical cells of two types. That means a cell which converts chemical energy into electrical energy is called as a chemical cell. Our mobile battery is a chemical cell. Lithium-ion battery. Lithium is a chemical that converts, it undergoes a chemical reaction and electricity is produced. Therefore, it's an example for a chemical cell. Chemical cell without transference. Two types of chemical cell. Chemical cell without transference. In this type of chemical cell, the liquid junction potential is neglected. A transference number is not taken into consideration. In this cell, one electrode is reversible to cation, while the other is reversible to anion of the electrode. See here, very important point, that is, in a cell without transference, in this type, liquid junction potential is neglected, or transference number is not taken into consideration. What is transference number? It's also called as transport number. We talked about salt bridge. In salt bridge, we talked about KCl. K plus ions move towards cathode, Cl minus ion move towards anode, we learned. That is not considered here. That's what they say, liquid junction potential is neglected. Transference number is not taken into consideration. So these kind of cells are called as an electrochemical cell without transference. In a chemical cell, the liquid junction potential is, or diffusion potential is developed across the boundary between the two solutions. This potential developed due to the difference in mobility of positive ions and negative ions of the electrolyte. See, difference in mobility. When we take KCl, the difference in mobility is not there because both moves with the same speed. But when you take any other electrolyte other than KCl, KNO3, ammonium chloride, ammonium nitrate, any other electrolyte, there will be difference in the liquid junction potential or diffusion potential. And that's called as an electrochemical cell with transference. Followed? See, this is not there in the syllabus. Electrochemical cell with transference, electrochemical cell without transference is not there in your cell. But concentration cell is important. This is very important, concentration cell. A cell in which electrical energy is produced by transference of substance from a system of high concentration to one at a low concentration is known as concentration cell. All right, concentration cell, very simple. We will try to learn the concentration. This is in depth. This is for competitive exams. Now we will learn concentration cell. What is concentration cell? What is this called as? Copper ions, and this is copper. Copper. What is this called as?
Half cell.
Copper electrode, half cell. Copper is half. Here also I have what? Copper and copper 2+. This is also copper electrode. This is also what electrode? Copper electrode. Here the concentration, assume that it's 0.1 molar. Here the concentration, assume it is 0.2 molar. Now these two electrodes are connected externally through a wire using through a voltmeter, and they are connected internally by means of what? a salt bridge. It's not clear. I'm not able to write it clearly here. This. So you understood the construction, right?
Yes, sir.
Electrodes are same. Electrolytes are also same. But what is the difference? Concentrations of the electrolytes are different. Those kind of cells are called as concentration cells. Generally, anode will be lesser in concentration compared to cathode. That is why a cell in which the electric energy is produced by transference of substance from a region of high concentration to low concentration. So current flows from cathode to anode always. So cathode will have more concentration than what? Anode. This is called as a concentration cell. We will learn concentration cell. See, this formula you should remember. This is called as Nernst equation. I didn't teach you Nernst equation. I will teach you Nernst equation. We spoke about the electrolytes. We'll have to learn with what? Nernst equation. Firstly, Nernst equation for a single electrode, how do we calculate? E is equal to E naught plus 2.303 RT by NF log of the concentration of the metal ion, log of concentration of the metal ion. This is the potential. This is the formula. This is called as Nernst equation. This is called as Nernst equation to calculate the single electrode potential. Nernst equation to calculate the single electrode potential. E is the electrode potential. This E naught is called a standard electrode potential. We defined what is standard electrode potential. R is a gas constant, T is a temperature, N is number of electrons involved, F is Faraday 96,500, C is the concentration of the electrolyte. Now see, for concentration cell, E naught will be 0. For concentration cell, E naught will be 0. I will tell you why E naught will be 0 a little later. Now for concentration cell, E cell is equal to 0.0591 divided by N log C1 by C2. See, our standard condition at 298 Kelvin and at 298 Kelvin, this value 2.303 into R value is 8.314, T is 298 divided by Faraday is 96,500. This value becomes equal to 0.0591. That's this value, 0.0591. And N is the valency. That's why at 25 degrees Celsius, you can write this value. This Nernst equation can be written as, E is equal to E naught plus 0.0591 divided by N log C at 25 degrees Celsius. Because all this is constant, temperature becomes constant, R becomes constant, F becomes constant. So that is what they have written. E cell is equal to 0.0591 divided by N log of C1 by C2. What is C1 by C2? C1 is the concentration of the anode and C2 is the concentration of the cathode. C1 is lesser than C2. Remember, C1 is lesser than C2. Understood what is concentration cell? The formula to calculate the concentration electrode potential of the concentration cell? Do not forget, yeah. Electrolyte concentration cell. Same thing. See at the same formula. Oh, here it is C2 by C1. C2 is RHS. RHS is cathode. I told you cathode is more concentration. I clearly told you. Here they have taken zinc as an example. Zinc C1 and C2. I took copper as an example. It's all the same. So anode concentration will be lesser compared to what? Cathode concentration. This is the formula to calculate the EMF of the concentration cells. So questions are there. We will learn questions on Friday, and any other. I will continue with the fuel cell, last part of the topic on fuel cells, maybe on Friday. Any clarifications? Batteries and fuel cells, we will do it on Friday. Possibly. So far, any clarifications, students? I was fast, but still I could able to justify, I feel. Any clarifications you have to tell me? Students, tell me quickly. Nobody is talking.
So once again, explain Nernst equation, sir.
Nernst equation we will learn. So first equation is given by the formula E is equal to E naught plus 2.303. Derivation is not there in your syllabus. 2.303 RT by NF log of the concentration. Now, 2.303 is a constant. R is a constant, gas constant. And if I take 25 degrees Celsius, it is 298 Kelvin. And I know Faraday is also constant. So this value will be 0.0591. So at 25 degrees Celsius, we can write Nernst equation to be E is equal to E naught plus 0.0591 divided by N log of C. When we work out the problem based on the Nernst equation, we will understand. This is called as Nernst equation to calculate single electropotential. We have to learn Nernst equation for an electrochemical cell also. That Nernst equation for electrochemical cell will be different. It's a combination of these two cells. We will be learning that in the next class. All right. Anything? Students, anything else? Ajay, any clarification?
No
Ritika?
doubt, sir.
No
doubt,
doubt.
sir.
How come, man?
Sir, I understood everything,
Hmm.
sir.
It really, you're just joking about, man.
Sir, no, sir. Really, sir.
Okay, good, good. All right, man. We'll meet on Friday. All right.
Yes, sir.
All right. I'll stop the class, madam.
Yes, sir. Thank you, sir.